Alright, let's do another compactness related exercise. And here there's not multiple parts to this exercise, so I can't do what I did in the last exercise where there was one part that I forgot to do, and I had to do part of it on the fly, and it was really messy and kind of a clown fiesta, so that didn't go as planned. But this one will be better, unless it isn't. So suppose U is open and C contained in U is compact. See here. So since U is open, there exists an open rectangle UX such that X is in UX and UX is entirely contained in U. So if UX happens to be of the form AI BI, then we're going to let Vx be slightly smaller. We're going to take AI plus xi over 2 and then xi plus bi over 2. Which ensures that both x's in Vx is contained in U. By the way, AI plus xi over 2 is the midpoint of AI and xi. So we're basically just shrinking the interval a little bit around the point xi. So it's still true that because x is still in Vx because each interval contains xi, and each interval is smaller than the corresponding interval for U, so it's in fact contained in U. Well, it's contained in Ux, which is thus contained in U. So. And this will also ensure that the boundary of Vx intersected with the boundary of U is empty. And this is why we had to choose a smaller index. And I didn't write a proof of this, but you could prove this without too much difficulty. Basically what you do is you choose any point in Vx. And you choose a neighborhood about that point. So here, let me do this visually actually. So for each I, we've got xi, then we've got ai and bi. So then we've got the midpoints. I'll call this ci and di. So ci is going to be ai plus xi over 2, and di is going to be xi plus bi over 2. It's not quite in the middle, but whatever. So you choose any point in this Vx. Let's say it's z, and let's say its index is here. So this is zi. Then what you can do is around this point, you can choose a neighborhood which is within ai to bi. So just like, I don't know, this would work. And so what you have here is you will have a, if you do this, so this could be di, ei, and fi. So if you do this for every single I, what you can do is find a neighbor. So for any point z in Vx, you can find a neighborhood. You can find an open rectangle containing zi, which is entirely contained in Ux. And so it's entirely contained in U. And what this means is that Vx is in the interior of U. And since Vx is in the... Wait. No, this is... We need more than this, actually. And I'll show you why we need this. But, in fact, we allow zi to possibly lie on the endpoints. See, I said that this didn't have multiple parts, so this would be a more straightforward solution. I guess not, but anyways. So zi could be one of the endpoints. Zi could be precisely ci. But because we've got some room between ai and ci, we can still put it in a neighborhood, which is entirely contained in ux. So if we allow z to be a point which is either in vx or here, because for all z in vx bar, which is, I was going to define this anyway in this problem, ai plus xi over 2 xi plus bi over 2. This is the closure of Vx. Well, I guess it's called the closure of Vx, and it turns out to be the intersection of all closed sets containing Vx. And that's not something that we need to prove here. We'll just call it the closure of Vx, and don't worry too much about that word closure and what that implies, because it does imply a whole bunch of stuff that I'm not going to prove, and that we don't need. But what we do need is that for every z in this set, z, there exists a neighborhood v containing z such that v is contained in u, which is, v is going to be contained in ux, which is contained in u. So the closure of vx is in u. And that's, so if the closure of v is in u, then okay, this will work. I'm going to continue with the proof and then come back to this if we need it. But the important point is that if you take any point in the boundary of Vx, it's not going to intersect the boundary of U. Because it turns out any point in the boundary of Vx is going to be contained in U, because the closure of Vx is contained in U. Okay, so anyways, let's move on for now. So then if we take the union over all x in U, yes. No? Yes. Yes. No. C. The union over all x in C of Vx. Wait. No. We do want U. I'm sorry. The union over all x in U of Vx, this is precisely U. And this contains C. So this is an open cover of C, so there's a finite subcover. There are Vx1 through Vxm, which cover C. All right. So see here, note that for any rectangle W, the closure of W equals W union the boundary of W. Okay, so now we're mentioning something which is actually useful for confirming what we said before. So the closure of W equals W union with the boundary of W. So why is this true? So if you take any point in the closure of W, so certainly each of these closed intervals contains the open interval. So any point in W is also going to be in the closure of W. However, what about the boundary? So if you take any point which is, if you take any point where one of the indices is precisely equal to the endpoints in one of the intervals, then you choose any neighborhood around that point, and in that particular index, the neighborhood will lie partially outside of the closed interval that's part of W, and part of it will lie inside the closed neighborhood in W. And this will hold for every single index. So if you choose the one that's inside for every single index, then you get a point that's inside of W. However, if you choose one of the indices to be outside the corresponding index, or the corresponding index for W, then the entire point will be outside of W. And so if you have equality at one of the endpoints, then you've got a point which is on the boundary of W. So for any point in the closure of W, it's either going to be in W or in the boundary of W. And similarly, you can prove that if you've got a point that's not in the closure of W, then it's going to be in the exterior of W. And that's because if it's outside of W, then it's got to... No, any point outside of W bar is contained in the exterior of W. And that's because if it's outside of W bar, it can't possibly even be on the endpoints of each interval. So each index of this exterior point needs to have some positive distance away from the interval for W. And so then you can put a small enough neighborhood around it that this small neighborhood will not intersect the neighborhood for W bar. And so you can prove that any point that's not in W bar or closure of W, you can call it either one, any point not in the closure of W is in the exterior. And so then you've deconstructed the space, and then you've characterized the entire space Rn, because points are either going to be in W, or they're going to be in the boundary of W, or they're going to be outside of W. And so that's how you prove that the closure of W is equal to W union the boundary of W. And that's how you know that the boundary of Vx intersected with the boundary of U is empty, because we've proven that the closure of Vx is contained in U. So the boundary of Vx is contained in U. And since U is open, it does not contain any of its boundary points, because any point can be completely contained within a neighborhood which is completely contained in the set, because it's open. Alright? So therefore, that helps us confirm that the boundary of Vx intersected with the boundary of U is empty, and yeah. So now, to find D, we want D such that blah 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 blah. The union, this is going to be precisely the union from j equals 1 to m of the closure of the Vxj's. Alright, so we want to prove that C is in the interior of D. So if X is in C, then there exists a J such that X is in Vxj. And this is precisely the interior of Vxj. But Vxj is a subset of the closure of Vxj. So the interior of Vxj is certainly going to be contained in the closure. No, the interior of Vxj will be contained in the interior of the closure of Vxj. And the interior of Vxj, well, this is contained in the interior of D, because the closure of Vxj is contained in D because D is just the union of these things. And so, C is in fact contained in the interior of D. Furthermore, now we want D to be completely contained in U. Since each Vxj is in U, and the boundary of Vxj intersected with the boundary of U is empty, the closure of Vxj is in U. Well, wait. What we really need is that this is the boundary of Vxj is contained in U. Well, wait a minute. Don't we already have this? Because so this is 0. Z is in this. There exists a Z and V such that this. So the closure of V X is contained in U. Yeah, we already talked about this. We already talked about the fact that the closure of Vx. We said that the closure of each Vx is in U, so the closure of each Vxj is in U. D is just the union of a whole bunch of things which are in U, and so it's itself in U. Hence, D is the desired compact set. And then, when writing up this exercise, I realized, oh, I didn't prove that D is compact. So let's prove that D is compact. So D is a finite union of rectangles. And so what you can do is, we actually proved this when we proved that closed and bound, no. We proved that compact implies closed and bounded. So when we prove that compact sets are bounded, we took a finite cover of this compact set, and we sort of prove that the union of a whole bunch of finite boxes can itself be contained in a box. And so it's bounded. Similarly here, D is a union of closed boxes, and that itself can be contained in a closed box, which, if you wanted, could be contained in an open box with a larger radius, but in any case, it's bounded. As for being closed, you can prove that you can prove that D itself is closed. Well, wait. Well, that should be easy, because we proved that the closure of D is U, or the closure of W is W union with the boundary of W. So the complement of W, the complement of the closure of W is, the complement of the closure of W is the exterior of W, which is an open set. So the closure of each Vxj is a closed set. And we're taking a union of closed sets. And it's a fact in topology that finite unions of closed sets are closed. But if you really wanted to prove it, what could you do? You take any point which is not in the union of the Vxj bars, and this point is not in each particular Vxj bar, and since Vxj bar is closed, there is a neighborhood about this point which does not intersect the vxj bar. Let's call this neighborhood uxj. So there's a neighborhood uxj about x which does not intersect vxj bar. And this exists for every j, and then take the intersection of all the uxj's. Then this will be an open neighborhood containing x. If you want to see why this is the case, you could write out all of these uxj's as intervals, and for each index, the left interval is going to be just the maximum of all the left intervals, and the rightmost and the right boundary of the interval is going to be just the minimum of all the right boundaries of all the uxj's at that particular index. And through that argument, you can see that the finite union of closed sets is closed. And so since D is a finite union of closed sets, it's closed. So D is closed and bounded, and therefore it is compact. And that does it. We've done the exercise. I'm sorry that I, again, have a really messy proof of showing that the closure of Vx is contained in U. I didn't really think it out as well as I could have when I was writing up this exercise, but hopefully this should at the very least give you enough information that if you wanted to turn this into a nice looking proof, you could. And with that, we're done.